Hi all, a very good evening.
Hello, hi sir. Hello,
Yeah, I can hear you.
sir. Like we can start in 3 minutes. More people can join after that.
Your voice is breaking. How you guys doing? I can see like a lot of people are yet to join. Are there any of the doubts in any of the previous sessions which we had earlier? If anybody has got any doubt, then like if you want to take it personally also, you can directly feel free to reach out to the organizing team, get them posted, and they can pass on the respective queries back to me.
Hi, sir. So I think so we can start now.
Okay, Archit. Okay, sure. Hi, all. A very good evening. And in this session of our Intro to Data Science, we will be deep diving more into the aspects of machine learning. Like last time, we had covered some of the parts on regression and classification on the algorithms like the linear regression, logistic regression, SVM, and naive Bayes, all those classifiers and regressors. So in today's session, we will be further deep diving into some of the other algorithms and be looking into some of the other robust algorithms which have been used in the recent times. Okay. So this is a continuation of yesterday's series on supervised learning. So today we will be looking further into the other algorithms which are there in supervised learning. And in the next week, we will be taking on the unsupervised algorithms which are there, like the k-means plus plus, k-mode, and all those clustering algorithms, which does not require any kind of a direct supervision or direct instruction from the label data. Okay. So this would be the agenda for today. We'll be covering on decision tree. So what is a decision tree and how to how does a decision tree work? What is information gain and what are the different pruning methods to prevent overfitting? And then we'll be picking up one of the common topics, which is the bagging versus boosting. So getting a detailed understanding of what is bagging and what is boosting and how does each of these algorithm works. And then we'll be taking a deep dive into random forest, which is one algorithm, which is a adaptation of the bagging technique. And then we'll be looking into the gradient boosted trees, which is an adaptation of the boosting technique. Okay. And then we'll be looking into the class imbalance thing and how to handle class imbalance in machine learning. Okay. And in the last part of today's session, we'll be looking into the hyperparameter tuning as what are hyperparameters and how to do hyperparameter tuning and what is the need of hyperparameter tuning in today's scenario. Okay. Yeah. So what is a decision tree? Okay. So decision tree is a type of supervised learning algorithm used for both classification and regression tasks. So it can be used for both. So unlike the other algorithms, what we had seen, like linear regression was only used for regression and logistic regression was only used for classification. Whereas some of the other algorithms like the supervised vector machines, support vector machines, which can be used for both regression and classification, a similar adaptation is the decision tree, which can be used for both classification and regression. So what it does is it splits the data into two subsets based on the value of the input features. Okay. Resulting in a tree-like model of the decisions. So whatever you see over here is a decision tree. So what it has got a root node. This is a root node. Suppose see we want to classify an animal based on the features it has, right? So the features, I mean that features like whether it has got feathers or not, whether it can fly or not, or whether it has got fins or not, right? So suppose say I am building this root node that if my criteria is the particular animal has got feathers, if it is true, then I'm looking to the other condition that whether the particular animal can fly or not. Okay. If the animal has not got any feather, then I'm going through this branch. So it is like a bi-directional thing, like it has got true and false. So it can be like multiple branches can also be there. So for the sake of this example, let's assume that it has got only two outcomes, that it is a true or false. Okay. So if the particular animal has not got feathers, then if it has got fins, yes or no, right? Can fly, yes or no. So if it has got feathers, if it can fly, then I can say that the particular example belongs to a hawk or an eagle. If it has got feathers and if cannot fly, then I can say that it is a penguin. So based on the four examples that I have, based on the three features like feathers, can fly, or if it has got fins or not, I can directly classify whether this animal belongs to a is a bird or a land animal. So the topmost node which is used for building the decision tree is called as the root node. Okay. So from the root node, what we do is we try to build up our decision tree. So these all things, these all nodes, what you see which connect, these all, sorry, not the nodes, these all branches which connect the two of the nodes are called as branches. Okay. And the intermediary between any of the leaf node and a root node is called as the internal node. And any of the nodes which does not have got any of the extended branches are called as the leaf node. So a decision tree consists of the root node, the branches, the internal one node, and the leaf node. So how does a decision tree work? Okay. There is something called as a splitting criteria. That means first we need to identify on what basis we can split up a particular data set. See over here, in this case, in place of has feathers, it could, our root node could had been like fly could had been my root node also. Okay. So from fly, I could have built the respective internal nodes, like whether it has got feathers or not, or whether it has got fins or not. Okay. And on that basis, I could have also built this particular animal classification thing. Or in other words, the fins could had also been my root node, and this can also would had been my internal nodes. So how to decide which of the features would be my root node or which of the features would be my internal node is dependent on something. What we do is on the splitting criteria. That means which features shall I take up, which would be giving much more information about the underlying data set. Okay. So some of the common criteria include the Gini index and the entropy. Much more on this we'll be discussing right now. So Gini index or Gini impurity is a metric used to evaluate the purity of a data set. Okay, so what is meant by purity? We'll be coming to that. So it is commonly used in decision trees to decide the best feature to split the data at each node. Okay, so based on the value, that is the Gini index value, what we are getting for each of the feature, based on that, we can say that whether that particular feature is pure or not. Okay, that gives a sense of purity in my data set. And the range of Gini index can go from 0 to 1, where 0 is it indicates a perfect purity and 1 it indicates maximum impurity. So for us, for any of the feature which needs to be used for splitting up our node should have got a value of anything which is near to 0, or if it is 0 then it's well and good. Okay, so if it is 0, that means that all of the elements belong to a single class. We'll look into the derivation of this, and with an example, I think you will get a detailed picture around this, as what is Gini index and how it can go to 0 and how it can go to 1. And if it is 1, then we say that all of the elements are randomly distributed across various classes. Okay, so keep this in mind. So Gini index is one of the values or one of the criteria through which we can say how to split up the nodes in a decision tree. So this is the formula of the Gini index. So for a node with n classes, it is calculated as 1 minus summation of I equal to 1 to n p of I whole square, where p of I is the probability of the element being classified into class I. Suppose say there are n classes in a particular data set that I have, right? And based on that, I am saying that what is the probability of the particular element, or the probability of the element of belonging to particular class between I equal to 1 to n. And for the number of classes that I have, I do a summation on all of it. Just remember this formula. Like, I think you can note it down. Let's see with this. Let's see for this with an example. Okay, suppose say a node has 10 instances. Okay, with 4 instances of class A and 6 instances of class B. Okay, so this is, say this is an example that I have got, and there are 4 A's and 6 B's. Okay, 6 B's are there and 4 A's are there. So the probability of A if I find out what is the probability of occurrence of A within this, that would be how much? 1, 2, 3, 4. That would be what? 4 by the number of elements. That is 4 by 10. Okay, 0.4. And the probability of finding B, if I randomly pick up any of the element from this list, if I want that it needs to be B, so what is the probability of occurrence of B? That is 6 by 10, because there are 6 elements which belong to B and there are 10 elements in the total list. So that is 0.6. So if I want to identify that how much pure, how much pure is my this particular list. Okay, so for that, what I will do, I will calculate the Gini index. So the Gini index value is 1 minus summation of I equal to 1 to n pi square. So there are two classes, right? I equal to 1 to n means I equal to 1 and then n is equal to 2. So for two classes, what would be 1 minus probability of a square and the probability of b square. So 1 minus 0.4 square plus 0.6 square, it is 0.48. So from this, we are saying that it is like in the midway between 0 to 1. So we are saying that it's a mix of classes in this node. So like this is a mix between the class A and B. Can anybody say me what would be the Gini index if I have got for A there are 5 and for B there are 5. Can anybody calculate this for me? There are 5 A's and 5 B's in a list of 10 elements. So what would be the probability of A? What would be the probability of A? Can anybody say me? Hello, am I audible?
1/2.
Yeah, it's 1 by 2. Okay. And similarly, for the probability of B would be 1 by 2 also, right? It is the same. So what would be the Gini index? 1 minus 1 by 2 whole square, right? Plus 1 by 2 whole square, right? So how much this would be? 1 minus 0.5 square. If I calculate that, 1 minus 0.5 into 0.5. Okay. So this is coming as 0.75. Is this correct? No, right? This is square 0.9375. So if I've got equal values for the class A and class B, that would come as 0.9375. So if in this element I have got for all this, I have got only A's, right? What would be my this Gini index? All the elements are A.
0.
0, right? 1 minus the probability of A would be what? 10 by 10? 10 by 10. That is what? 1. So 1 minus 1 is 0. So what this would say? This would say that the class or this total, this is totally pure. Okay, that means there is no impurity within this particular data set that I have. That means if I randomly pick up anything, I will be like, if I build any of the random classifier or any random model, the chances of picking up a particular class is always true, right? So this is 100% pure. That means it is 0. So if it is near to 1, that means if there is variability within the data, so as you can see that 50% of the data is A and 50% of the data is B. So it is near to 1, which says that there is impurity within the data. So if I try to pick up any of the class from here, then it becomes difficult for me to which pick up like which element. I'm not sure on that. Let's see for the other example. So here we had seen what this is Gini index. So you could also say that I could have also taken as 1 minus for Gini index 1 minus sum of I equal to 1 to n pi. Can anybody say me why did I took the pi square? Has anybody got this doubt? Like for calculating the Gini index, we could have also omitted this square and could have gone ahead with the only the absolute value of that. How does adding a square root help? Anybody has got this question on top of his mind, like, are we, why do we need to add this square term? If not square, like, could this had been done as well, like the Gini index could had been calculated, right? Because as the case we had seen, 1 minus 1 was 1 minus 1 square is similar to 1 minus 1 also. Just what I would say is just research around this. So why we are taking a square term while we are calculating the Gini index? Okay, I think you will get much more clarity on this. If you like don't get all those answers for that, then feel free to reach out to me. We can discuss on this. So why we are adding this square term, and if not square, we could have got like ahead with a cube or a quadrant. Yeah, someone is telling. Hello. Yeah, Pratik. Hello.
Hello, am I audible?
Yeah, I can hear you.
I was taking a guess about y square. I think it's because so the values when summed up lie in between 1 and 0.
To get it between 1 and 0. So this would anyway be between like
Because
the
because probabilities are basically fraction, right? So when you square them, you are basically decreasing the value.
okay. Yeah. So see, the probability would anyway be positive number. This 4 by 10, 1 by 10, or 10 by 10. This would 0 by 10 to 10 by 10. That would anyway be a positive number. Okay, so like as Pratik took this initiative, so let me clarify that. So the reason behind taking a square term is that we want to penalize for the higher probability terms. That means suppose say a class is occurring most of the time. Suppose say A has 2 terms and B has got 8 terms. Okay, A is 2 and B is 8. So for the probability of finding of B is 8 by 10 or 0.8. So naturally it would drive my Gini coefficient value much more lesser, because if I take the 1 minus 0.8, it would be what 0.2. So the majority of the class, not to have a major impact on my model, what I do is I take a square of that. So it becomes 0.64. Okay, 0.64. So that the majority class does not have that much impact on my Gini coefficient value. Similarly, if it is 0.9, so it becomes 0.81. That means we are decreasing the effect of the majority class. And similarly for the classes which is low, that means suppose say for A is what 2 by 10, it is what 0.2. 0.2. For this, if I take a square, what would be that? 0.2 into 0.2. This would come as 0.04. So for the minority class also, we are again diminishing the effect of that. So for the majority and the minority class, we are diminishing the effect. That means we are trying to play a balance between the influence of the majority class and the minority class in the data set. Okay. Otherwise, like you could have also taken the cube term, quadrant term. anything as such, but mostly people go with the square term. Hope this clarifies. And the other information like how to have the best split index, right? The if you have like not forgotten the main idea behind using of the Gini index and the uh, other parameters like the entropy was to find out the best split of the data set, best split of the features which can be my root node. Okay, so for that purpose we are only going ahead and calculating all these things. So the other thing what can be used if in not of the Gini index is the entropy. So the entropy, as most of you might have learnt in the physics, is a measure of the amount of uncertainty or the randomness in a data set. Okay, this calculates the randomness in any of the data set. So in the context of the decision tree, it quantifies the impurity or the disorder in the set of examples. Similar to the data set what we had, we can use the same, but the formula for entropy is something different. So the range value is from 0 to log base 2 n, where n is the number of classes. And similarly, if it is 0, it indicates that it is perfectly pure. That means it is pure data set. If it is maximum entropy, so the maximum is log base 2 n. So based on the number of samples I have, suppose I have got 3 classes, right? So for 3 classes, it would be log 2 of 3. It would be 1.58. So if it is near to 1.58, then it is not that impure. That data set is not that pure. If it is near to 0, then I can say that the data set is pure. Okay. So the formula for entropy is minus summation of I equal 1 to n pi log base 2 of pi. Can anybody see me like similar kind of a thing we have done in some other calculation yesterday while reading one of the other algorithms? We had taken similar kind of a cost function to calculate the losses, and something similar to entropy was also used over there. So if you remember the logistic regression, there the cost function what we had used was the log loss, right? Or it was the binary cross entropy function. There it was cross entropy and binary cross entropy. The reason behind binary cross entropy is binary is 2 classes, and cross entropy is we are taking the cross of the probability of occurrence of one class as compared to the other class. And here it is entropy. So the probability of pi to the power pi. This is what is there for the entropy. And I had taken a log on top of it. So if I take a log of this would be what? Pi log pi. Pi log pi. Okay. And for every classes that I have, like suppose I have 2 classes. So this would be what? P1 log P1 plus P2 log P2. Okay. Let's take an example. For the similar example, what we already had, like 4 classes, 4 values belong to A and 6 belong to B. Right. So if I calculate the entropy, so it would be what? PA log base to PA plus PB log base to PB. This is what PA was 0.4, probability of A was 0.4, probability of B is 0.6. So I'm getting 0.972. So what had I told? Like for 2 classes, log 2, 2. What is the value? It is 1. So it is coming near to 1, which says that there is a impurity within the particular data set. So using Gini index, it is saying that there is a mix of impurity. It is not pure, but here it is saying that it is mostly impure in this particular data set. Okay. But these two are not comparable to each other, like entropy and Gini index. We can't compare uh, one with the other. The only thing is either you can go ahead with Gini index and look into the value. If it is coming near to 0, then it's good. If it is coming near to 1, then we need to discard or use any other features. Okay. Similar to entropy, but the entropy range is different. It goes from 0 to log base to n. Suppose say we have got this particular data set, right? There are 14 instances, and this is particular feature which is the weather feature, like whether it is sunny, rainy, overcast, cloudy. I don't think we have cloudy, sunny, rainy, overcast. And the other feature is the temperature of the particular day, right? And suppose we have got a class that whether it is we can go out or not, right? Suppose it is sunny and it is hot, we are saying that we can't go out. And suppose it is overcast, it is hot, then we can go out. It is weather is rainy and it is the temperature is mild, then we can say we can go out. So how can I build a model on top of it? How can I build a decision tree on top of it using all this feature one and feature two? And which of the feature, whether the feature one would be my root node, right? Or my feature two would be my root node. How to identify that? For that, what we will do is we will calculate the Gini index or the entropy for each of the features and find out like for which of the feature the Gini index is the lowest, and based on that, for if it is lowest for feature one, then we will pick up feature one as my root node. If it is lowest for feature two, then we will pick up the feature two as my root node. Okay, let's do the calculation. Suppose if for feature one, okay, let's calculate first the Gini index. So for sunny, like for everywhere it is sunny, right? Let's mark that as red. So for sunny, 1, 2, 3, 4, 5. Five instances we have where it is sunny. And for sunny, where it is no. So this is a no, this is a no, this is a no. And so we have got three no's and how many yeses? Two yeses, right? When it is sunny. When the weather is sunny, we have got three no's and two yes. Okay. So for sunny, there are five instances. We have got three no's and two yes. So for Gini of sunny, Gini index for when it is sunny, what we have to do? 1 minus P of I, summation of P of I whole square, right? P of no whole square plus P of yes whole square, probability of yes whole square. So probability of no would be what? It would be 3 by 3 plus 2, 5. And for yes is what? 2 by 2 plus 3, 5. This is what is coming. And for sunny, it is 0.48. And similarly for overcast. When it is overcast, what are the values? Like for overcast 1, 2, 3, 4. For overcast, it is yes, 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 yes. Okay. So we have done this, right? When in that particular, so for overcast, it is 5, yes. So when all the values are same, what would be the Gini index? Can anybody say me? That means there is no impurity within the data, right? That means it is all pure. So for when it is overcast, it would be 0. Got it? And when it is rainy, so for rainy, this is a mix like 2 no and 3 yes. So it would come as the same like 3 no, 2 yes is the same as 3 yes, 2 no. So it would come as 0.48. So weighted Gini index for the feature one. So weighted Gini index for this feature would be the weighted average of all of this Gini indexes. Okay. So for sunny, so for sunny was occurring out of 14 instances, 5 instances had sunny. So 5 by 14 in Guinea of sunny and 4 of 14 by Guinea of overcast and 5 by 14 of Guinea of rainy. So if I do this average of weighted sum of all of this, then my Guinea index for feature 1 would come as 0.342. Okay. Is everybody clear like how I calculated the Guinea index till here?
Yes, sir.
Okay. Yeah. So for the feature 2, for the first feature, this was the supposedly the weather feature, right? And this is the temperature feature. So for the weather feature, I have got that the Gini index is this much. And similarly for the feature two, like for hot, whenever it is hot, like this is hot, 1, 2, 3, 4, right? For 4, like how many when it is hot, right? How many yes and how many no? 1 yes, 2 yes, 2 yes, 2 no. So this is a balanced this thing. So it is a balanced like a split between both. So it is coming as 0.5. Okay. Similarly, when it is mild, 2 no, 2 yes, 0.444. And for cool, so this is we are calculating for the second feature. We had calculated for the first feature. For cool, it is 0.375, and a weighted sum of all of that would give me a Gini index of 0.440. Okay. So which of this is lower? For feature 1, the Gini index is lower. 0.342 is lower as compared to the feature 2, which is the temperature. Similarly, if I calculate the entropy, I know the probability of occurrence. So entropy calculation is what? Minus summation of I equal to 1 to n probability into log base 2 of probability. Okay. So this is the same way I had calculated for the entropy for all of the features. So for sunny, it is this much. And for overcast, as we know that it is same, so it is coming as 0. And for rainy, it is this much. So the weighted feature is 0.694 for feature 1, and for feature 2, it is coming as 0.911. So the summary, like for feature 1, we have got a Gini index of 0.342, and for feature 2, we have got a Gini index of 0.440. Similarly, for feature 1, we have got an entropy of this much, we have got an entropy of this much. That means there is less impurity, or it is more pure, less impurity for the feature 1 as compared to the feature 2. Similarly, there is less randomness within the feature 1 as compared to the feature 2. So is it, this can be sufficient for us, right, to take up feature 1 for my building up the root node for the particular model. So based on that, feature 1 weather is the better choice for this first split in the decision tree because it has got lowest impurity, indicating that it provides a clearer separation of the classes compared to the feature 2. So suppose if I have taken a feature 2 over there and I have built this kind of a uh, decision tree, then it would had not been helpful. So how my this would be right now? Let me clear this. So what was my feature 1? Feature 1 is my say weather, right? And this is temperature. So my decision tree would look like what? This is weather, my root node. And for this, whether it is sunny, right? Whether it is hot, and whether it is, sorry, not hot. Whether it is sunny, rainy, and overcast. Right? There are three classes: sunny, rainy, and overcast. So for sunny, what I will look again, whether it is hot, mild, and cold accordingly. So this would be my leaf node, the feature 2. Based on that, I will calculate whether my output would be a yes or a no. Okay. So based on all of these features, I will calculate, build a decision tree out of it and see what is my corresponding output. Okay. So this is how I calculated and got to know like what would be my root node for my particular decision tree. So like I can start with the feature 1 as my root node. Okay. So for the other features, like what should be my internal node? So for internal node also, I need to calculate like what should be the other feature I can pick up, and then I can split it up. Suppose say in this case, right? In this case, so this root node was what? Internal node was can fly or has fins. So how to select which should be my internal node? If there are some multiple features within the particular data set, and I have to narrow down on any of the one or two particular internal nodes only. So for that, what I need to look is into the information gain. So the information gain is a concept used in decision tree to finding the most informative feature to split at each node. Okay. So the formula for information gain is the entropy that I have calculated at the parent level minus the ni by n, where ni is the number of instances in the ith child node and n is the total number of instances in the parent node. That means the number of samples that I have in the child node versus the number of instances which is there in the parent node. So the parent node was what? Has got feathers or not, right? And ni is the number of instances in the child node. So the child node is the whether it can fly or not. So the number of instances, I can do a ratio on top of it and can calculate the entropy in the child level. So the child is the node what I am looking. So from this, just a second, I'm getting a call. Yeah, guys, I'm back. So for that, I have to calculate the information gain. And for each of the child nodes, I will reiterate through each of the child node. And I will see like for every node or for every features, what is the information gain that I'm gaining from each of the particular feature. So for where like I will be getting the highest information gain that indicates that the feature provides much more information about the classifying the data. That means what? It has led to the greater reduction in entropy in my particular node, right? So always my information gain would be, I need to look up like for each of the feature, if my information gain is higher, then I can pick that particular feature and make it as my internal node or my child node. Okay. So for the root node, what I will do is I need to look for first the Gini index or the entropy. And based on the Gini index or the entropy, I can build the root node accordingly. And after I have built the root node, then I will find out the information gain. So root node or the parent node, right? So for the parent node, I know the entropy, and from the entropy of the parent, I will for each of the features, I will find out like what is the particular information gain that I'm getting. If I'm getting a particular highest information gain, then I can use that particular feature and keep that as my next available internal node or my next available child node. Okay, that is how you will be building a particular decision tree, and the decision tree can be used to build any of the classifier model or any of the regression model. So whatever we have understood till now is based on probability, right? And for probability, the output was either 0 or 1. So in this case, it was either 0 or 1, right? Was a classification thing. But in the starting, I had also told you like decision tree can also be used to build a regression model also. So to build a regression model, there we don't go ahead with the Gini index or the entropy, there we go ahead with the finding the losses. That means how much is the mean average error or the mean square error at the root node. So based on that, we try to find out for which feature it is giving the less mean square error. For that feature, we can pick that and make it as the root node and the other as the in an iterative fashion, we can go ahead and select the other as my uh, internal node. Hope that clarifies. So if you would see like a decision tree, we are building it step by step. So what happens is that if we have got much more noise in the data, then our decision tree would evidently pick up that particular noise and would build the branches or the nodes in such a way that it mimics the underlying behavior within the training data. So that would lead to the overfitting. So to remove around that, what we can do is the method available in decision tree is known as pruning. So the different techniques how we can do the pruning is the pre-pruning. So pruning, like you might have understood, right? Pruning is what we do in the case of gardening. We prune the branches of the tree so that we don't want the tree to grow any longer. Or prune the branches in a certain direction. That means we don't want to grow it in that direction. So similar concept is applicable on the decision tree also. Think about like we are we have built this particular tree, right? We are limiting that the number of the depth it can go. That means we want that it should not go much more than the three levels. Okay. If it is this is the first level, this is second level, I don't want it to go much more than the third level, because I know that if it grows more than that, then it would lead to overfitting. And the minimum number of samples per leaf. Suppose say under this there are two, right? Under say this are three, under say this are four or five. I can also limit on the number of samples. So if I limit the number of samples per leaf or limit the this should be the minimum number of samples. It should have at least two number of branches in that particular tree. So based on that also I can reduce the overfitting in my tree, in my decision tree. And the information gain which I am calculating, I know that the particular information gain which I have calculated need to be more than this particular threshold. If it is less than that, then I am not considering that particular feature for building my decision tree. So the other techniques, like these are pre-pruning techniques, and the other techniques are the post-pruning techniques, like reduced error pruning, cost complexity pruning. Like if I've got a cost function on top of it, and based on the cost function, I am removing certain branches. That means I don't want this particular branch, or I don't want this particular branch, right? And the subtree replacement. For this tree, I can replace this with any other particular tree, which I see that this tree is not at all helpful for me. I can remove this branch, total branch, and I can build another model all in, like from scratch. Let's see an example of how this is done in Python. Okay. For this, we have taken up a sample data set on the student data set, which says that the number of hours the student has studied, the attendance, the previous grade, and whether the student has passed or not. Okay. Similar to what we have done earlier also. So these are the different libraries which are needed. So from scikit-learn, you will get the decision tree classifier, and I think all of the other are already available to you. The trend test split, the classification report, confusion matrix, and all those things. Okay. And I am preparing my data. So my x's are what? All the features are hours studied, attendance, and the previous grade. And the y is, let's print that df. So this is my output, and this is what is my input, hours studied, attendance, previous grade. So from this, what I will do? Can anybody say me what is the first step I need to do for building that particular decision tree? I need to find out which is my root node, right? Whether it is hours studied or attendance or the previous grade. Which of this would be important for me to build the root node for my particular decision tree? So all of these are integrated within the particular library what you have. You don't have to explicitly do that like iteratively. All of these are integrated within Python. So that would give you the total output. So in the classifier is equal to decision tree classifier. Here, if I do an expansion of it, so here you can see that the criterion is Guinea. So in place of Guinea, I can also give the criteria as my entropy also. And the maximum depth, which I was talking earlier, the minimum sample split, minimum sample sleeve. These are the different values which are there. So more on this we'll be discussing in the last part of today's session on the hyperparameter tuning. So these are considered as hyperparameters. These are the things which constitute or which essentially dictates as how my decision tree would behave. If I increase one and decrease the other, then it can lead to overfitting, or it can lead to underfitting also. So how to balance all of these hyperparameters is something which we will discuss later. So this is a classifier which I have built, and I'm predicting on that. So I'm getting an accuracy of 0%. That means none of those are correctly classified for me. Okay, it is 100%. Let's build the confusion matrix. So this is a confusion matrix That means all of the classes. So there are three instances in the test data, and all of those are correctly classified by my model. Let's visualize the decision tree. So if I plot the decision tree, this is how I'll get. So my root node is the hour studied. Okay. So the Gini index for this was coming as 0.49. And given that this is a continuous variable, what we have done is we have taken an average out of it, and based on that we have splitted it. Okay. So anything which is less than 5 is going to the left, and anything which is more than 5 hours is going to the right. So for less than 5, this is my root node, and for more than 5, this is my sorry, the leaf node. These are the two leaf nodes. So from the this thing, I am calculating again the Gini index, calculating the information gain, and based on that, I am trying to predict whether it belongs to fail or pass. Okay. Coming to the other thing of the application of decision tree is the bagging and the boosting techniques. In decision tree, what we had seen is we are trying to build a particular tree from scratch, which has got a root node, a leaf node, and the other output from the leaf nodes. And those can, like, what it generally happens in decision tree is, like, given that we are mostly looking into the training data and doing it iteratively, it tries to overfit on the training data. Even with the method of pruning and all those things, still that overfitting and underfitting techniques are mostly evident within the tree based models. And sometimes, like, if we increase the complexity of the data, like if we use more of the data, then my performance of the decision tree decreases. And the reason behind taking decision tree as compared to linear regression is, in decision tree the computation is much more faster and much more efficient as compared to linear regression. In linear regression, with by doing the uh, 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 all those available assumptions what we had seen, right, like the data needs to be linear and all those things, in decision tree all those assumptions are not valid. Here we can directly take nonlinear data or categorical data or any of the data what we have, and the model gives the best result. In those cases, we are generally going ahead with a decision tree. But some of the more advantages what we get is by the use of this ensemble methods, like the bagging and the boosting. So what is bagging? Bagging is a, like, acronym for the bootstrap aggregation. In bagging, what we do is, our aim is to reduce the variance of the base learning algorithm by training multiple models on the different subsets of the training data. So for a particular sample that I have, so this is, say, my training data. Okay. So for this, what I'm doing is I am creating different samples out of the particular training data. This is one sample, this is one sample, this is another sample. So if I club all of the samples, that would be a sum of, that would be signifying to this particular training data that I have. Okay, I'm differentiating that into different samples. And on each of the sample, what I'm trying to do is I'm trying to build a particular decision tree on top of it. Okay. On each of the samples, I'm trying to build a decision tree on top of it. So how it helps is, we are distributing the data. And by distribution of data, what we are looking is this model, the model which is built, this model 1 is independent of the model 2 on this sample, whatever we have. And this model 1 and model 2 is independent of the model 3. So we are generalizing for the data what we have. So our training data, even if that is a one single data, we are splitting that into multiple pieces. And our aggregation of the model what we have is quite generic as opposed to a single model if we had built it on the training data. So in that way, we are reducing the variance. Okay, if we remember yesterday, we were discussing on that, right, the bias variance trade-off. So if the highest, more is the variance, then the model is overfitting. So by decreasing my variance, I am trying to underfit my, I am trying to reduce the overfitting on my particular training data. So this is the process how we are trying to do. First, we are trying to create multiple subsets of the training data that are created by sampling with replacement. Okay. So that's why the bootstrap sample. So from this, we are bootstrapping and sampling the data. So that's why the name the bootstrap is coming up. And then we are combining. That means the combination of the final prediction is by averaging for all the values, like for each of the model what we have. So for model 1, model 2, model 3, the output we are aggregating. That means suppose model 1 is giving us 0, this is giving us 1, this is giving us 0. So out of that we are aggregating, we are averaging out of it or taking the mode out of it, right? And then we are seeing that whether what would be the output of the total model. So that's why first we are doing the bootstrapping of the sampling of the data, and the other is the aggregation. So there are two steps which are involved. One is the bootstrapping and the aggregation. So that's why it is called as bagging technique. So the advantage what we had earlier discussed is it reduces overfitting and works well with unstable models prone to variance. Okay, like decision tree which was prone to overfitting, we can remove that. And given that this is parallel model, so model 1 is independent of model 2 is independent of model 3. Given that I have got a huge amount of data, I can distribute all of this. In one computer, I can train my model 1. In another computer, I can train model 2. So if I have got 50 different models or computers or clusters, I can train it parallelly and create different models out of it, so that it reduces my computational uh, uh, so it reduces my computational whatever spend we have. Okay, so that way we can get a better model at the end also by utilizing the computational power, all of the computational power what we have. So it reduces the time of computation. So one of the examples of bagging technique is the random forest algorithm. The other algorithm, other ensemble algorithm what we have is the boosting. So in bagging what we have done, we were trying to split the data and try to build multiple models out of it. Where in boosting, we are trying to iteratively improve the performance of weak learners. Okay, first we are trying to train a weak learner, and based on the output of the weak learner, we are trying to train another learner on top of that for the misclassified examples. Okay, suppose say I have got this particular decision tree. Okay, model 1. So our model 1 has predicted for, suppose say there are three classes 0, 1 and 2. So for 0 and 1 it is predicting well, but for 2 it is not predicting well. Right. So what I can do is I can take all the samples from model 1 and build another model called as model 2. Right. So model 2 takes all the features which are there for corresponding to this particular thing. And on this, I can build another decision tree on top of it. I can build another decision tree on top of it, so that I know that this is only biased towards all the misclassified examples. That means I treat this as a single class and treat this as a other class. And for this, I am making my model to biased for the features which are there for class 2. And using the output of model 1 and model 2, I can say that the aggregation of all the output would be my final output. So the combination process is the same, like for all the weak learners, we are trying to do the weighted sum. Okay, based on the number of features which are there or number of instances which are there. So the advantages are like it works well with stable models like prone to bias. So there in bagging, what we were trying to reduce, we were trying to reduce the variance, but in boosting, we are trying to reduce the bias, which means that some of the models are underfit. See over here, like model 1 was underfit for classes which belong to 2. So that's why we had removed this and made this as a another model over here. That means we are reducing the underfitting problem. That means we are reducing the bias. And similarly, given that this is a aggregated feature kind of a thing, so it is also reduces the overfitting. So in most of the cases, what you will see is sometimes we go ahead with boosting and sometimes we go ahead with bagging technique. But boosting is generally much more helpful given that it targets both. It reduces underfitting, it also reduces the overfitting problem as well. So the various examples of boosting technique are like the add a boost, gradient boosted trees, or cat boost. So this is an example of bagging technique. Suppose like this is the model one, this is the initial model, and so for that we have built three models: model one, model two, and model three. Sorry, these are the models, these are the data sets. So for this particular data, what we have done is we have splitted that into three parts, right? Three samples we are taking, and for each of the sample we are building three different models. And for three different models, by doing a weighted sum or an average out of it, aggregation operation, we are getting the final output. While in boosting the same particular data set, we are building one particular model, model one, and based on the output of model one, we are taking the same data set and building the model 2 on top of it. And based on if there are further misclassified samples or misclassified data where the error is coming up, we pick up those, and based on that, we are building another model 3. Based on aggregation of model 1, model 2, and model 3, we are getting the final output. Okay, so this is a sequential operation and this is a parallel operation. Any doubts till now? Okay. So the main difference between bagging and boosting is bagging aims to reduce the variance or the overfitting problem, where boosting tries to reduces on the underfitting problem. Okay. And the other is the independence. In bagging, models are trained independently. We can parallelly build those models over here. Like these models are independent to each other. But in the other case, in the boosting, those are sequentially. That means one is trained one after the other. So if you want to develop a parallel mechanism to train all those models, then it is not possible in case of boosting. It is possible in case of bagging method. And the combination method. So bagging typically combines the prediction using averaging technique, while boosting combines through the weighted sums. Okay. And the robustness, what we had also discussed, like on the overfitting thing, like it is much more robust as compared to the decision trees. So one example of the bagging technique is the random forest. Okay. So random forest, what we do is, this is an example of a bagging technique wherein we are building for the same data, we are having three different instances and building three different classifiers on top of it. And by using a majority voting of all of the output of three different, so this is one decision tree, this is second decision tree, this is third decision tree. So by using an aggregation operation of all the three different decision trees, we are getting a final output. In case of classification, in case of a regression, we can take the mean prediction, the average prediction for all of the different individual trees. Okay. So the advantage what we get in random forest as opposed to the any of the bagging technique is, in we are looking out for random feature selection also, which was not present in the case of a bagging technique or in the decision tree. That means suppose say there are three different features. So this is y and these are x. Okay, x1, x2, and xn. Okay, so there are say n different features. So while building the random forest, although we are looking into although we are taking up samples of data, right? So for this there would be one decision tree, for this there would be another decision tree. Along with this, what also we are doing is, in this we are also splitting it up column wise. That means the decision tree 1 can have only x1 and x2, while in decision tree 2 it can have x2 to xn. Okay. So random feature selection also we are trying to do. So through this way, what we are trying to do is, we are trying to reduce the overfitting problem. So this is the main advantage what we get through the random forest as opposed to the other backing techniques or other decision tree algorithm as well. Let's see an example of how this is done in Python. So for the same data set what I had earlier, so by using the ensemble library of scikit-learn, there is something called as random forest classifier. And on top of that, I'm building a classifier. So for this, there are the different hyperparameters. So these are the number of estimators, the number of the criteria like Gini index or the entropy, the maximum depth of the particular classifier, the number of samples played, the number of samples in the leaf, minimum weight fraction. So these are different hyperparameters which are there. So out of box score, and these are other like to print whether how my model is training, how much error is coming up. So if I build that thing, then the accuracy is still, it is one, because this is a small data set, so it will not be that much different for a decision tree to random forest. But in general, random forest is much more good and much more robust and gives a better result as compared to the decision tree. And if I print that particular decision tree, so given that it was not that much data, otherwise it would have printed multiple decision trees. And coming to the other technique of the boosting mechanism, which is called as the gradient boosted trees. So if you remember in the bagging technique, what we have done is we have looked into the random forest, okay, where it was trained parallelly. That means we are taking a sample of data and training it. But in gradient boosted trees, this is a boosting technique. In boosting techniques, what we do first, we build a basic weak learner or a weak classifier. And based on the predictions that we have, we do the weighted data. That means some of the samples we pick it up and club it together and build another weak classifier on top of it. So this is how it is sequential operation is done on top of it. So the naming behind gradient boosted trees is it uses gradient descent optimization to minimize the loss function, which is typically the mean square error for regression task and log loss for the deviance or the classification task. So while calculating the root node and leaf nodes, what it does is, for regression, we already know, right? We need to have the mean squared error. And for this, in place of the Gini index or the uh, entropy, it goes ahead and find out the log loss. Okay, so that is the basic difference between the any of the boosted trees and this gradient boosted trees. And based on the weighted sum of all of the individual decision trees, I can find out what is the output for me. Okay. And there are different kind of gradient boosted trees which are available for different applications. So one of those is the XG boost, extreme gradient boosting. The other is the light GBM. And the third is the CAT boost. Similarly, there is ADA boost also, adaptive boosting. So XG boost, what it does is it has got the implementations of the L1 and L2 declaration, which can further reduce my overfitting problem. And in light GBM, so mostly what we use in the industrial applications is the light GBM. So light GBM is quite fast in computation and it has been like developed by Microsoft. So it has got a novel implementation which is called as gradient based one-sided sampling. That means while selection of the data, if you remember in the bagging technique, we were using with the random forest, we were taking the samples of the data, right? For this, we were taking the samples of the data, decision tree one, decision two. These are the samples of data what we had taken for my application. So the same thing is also used in gradient boosted trees in the light GBM application, like gradient based one-sided sampling, and the exclusive feature bundling technique, which reduces the memory usage. That means some of the features we are taking like collectively and building a model on top of it. The other application, like if we have got more number of categorical variables, then the best way is to go ahead with the cat boost uh, algorithm or the cat boost based tree. In this, it automatically does or handles the categorical variables without the use of any particular uh, category embedding techniques like the one-hot encoding or the label encoding. And like there are other applications also like the AdaBoost and the other applications which I think like the more you research, the more you will get. And there are different like versions of this particular boosted trees are also coming up, which are giving further different like good results with time. Let's see how you can implement a gradient boosted tree. So similarly in scikit-learn.ensemble, we have got the gradient boosted classifier on the same data set which we had built up. We will fit the particular model, and based on that, we'll get the accuracy, the confusion matrix, and the classification. Let's erase that. So over there, what I had told, like in other cases, we were calculating the Gini index, right? Gini index over here, given that this is a gradient boosted classifier. Here we are calculating the mean square error. Okay, mean square error or the log loss, given that this is a continuous variable like the attendance, the data I don't have right now. The attendance is a continuous variable. The hours studied is a continuous variable. Previous date is a continuous variable. If I would have got a categorical variable, then I would have gone ahead with the log loss. Because these are continuous variable, I have gone ahead and have used the mean square error. So here I am getting the mean square error for this particular value. Like for attendance, this is a particular mean square value which was less as compared to the other hours studied and the other feature. So based on that, if the attendance is less than 50, I'm taking the left sample. If it is more than 50, I'm going ahead and building the right branch of the particular gradient boosted tree. So one of the common things what we generally see while building any of the particular classifier model, anything, so starting from the naive-based classifier, logistic regression, right, to this decision tree, random forest, light GBM, and all those things. Has anybody got any of the doubt till now before we go ahead to the class imbalance thing? Okay. Yeah. So in class imbalance, so what we had seen is like in any of the real world scenarios, if you would see, like say there is bank fraud happening, right? So out of say 100 samples which we have collected, so the number of frauds which is happening is quite less, right? Suppose say we have got 1 lakh cases what we are looking into right now. So for 1 lakh samples might be there would be 100 cases where people might have done a fraud. Okay, but in other 99% of the data there is no fraud. So there is obviously a disparity between the one class versus the other class. So if say this is the fraud data, right? Probability of occurrence of fraud. So this is like not occurrence of false rate of fraud if I take the bar of it. So this is like all of the instances where it is not occurring any of the fraud. And for the fraud to occur, it is quite less. That means it is 1% of the chance it can occur. And in 99% of the chances, it will not occur. So if I try to build any of the classified model on top of it, my model which is there, it would always be biased for the majority of the classes that I have, because most of the features which are there are significant or are mostly for this particular thing where it is not a fraud. It is zero and this is one. Okay. So where it is zero, my model would be much more biased towards the majority class as opposed to the minority class. So that is what is known as class imbalance. That means the any of the thing what we see in real world scenario or any of the application, there is highly imbalance within the particular data. So how to handle the class imbalance thing? That means how I can build the model in such a way so that my model is not biased for this thing, and it is like highly unbiased for both of the data. That means anytime it should give me the best value out of it. So one of the technique is the resampling technique. That is the undersampling and the oversampling. Okay. What do you mean by undersampling? Suppose say I have got a majority class M, majority class 1, which has got 99% of the data. Sorry, not 99%. Let's make it uh, for this. Suppose it is 70% of the data. This is majority. And for minority, it is say 30% of the data we have, right? So what we can do is undersampling. That means we can reduce this from 70 to make it as 40. Okay, that means we can undersample this so that this and this, so like 30% and 40% are nearly like in the same terms, and those can be used to build my model. That means I am removing some of the features from my data. Okay, and the other is the oversampling. Suppose if from 30% I can make this to 60%, right? That means I have oversampled this data. That means I have replicated more of the data points where the class value is 0. So there are various techniques how you can do the oversampling. One is the random oversampling. That means I can just replicate the data, whatever feature I have, I can just create a copy out of it. Okay. And the other is the SMOT, or the synthetic minority oversampling technique. So in SMOT, what we do is, suppose say I have got this feature, right? Like 1, 2, 3, and dot dot dot. I know there is a linear relationship for these classes. So for all of the feature, it is 0. The target variable is 0. So I know that it follows a linear distribution. So I can create other samples as well. Like if I make it say 90, another feature value which is 90, 91, 92, and similarly. That means I am creating synthetic features out of it for the same class, and I can assign the same class as 0. That means I know that there is a linear relationship between the target and the input. So that is what SMOT does. SMOT, it synthetically generates much more data by looking into the k nearest neighbor which are there for my particular data. Suppose say 1, 3, 4, 1, 3, and there is 5. So for these all things, I know there is a linear relationship. So I can create another feature which is 4, right? I can create another feature which is 4 and can give a target as 0, so that it artificially we are generating more data. Similar technique is ADASYN, which is adaptive synthetic sampling. Similar to SMOT, this is where we are synthetically generating more of the data. And there is combined sampling also, like a mix of undersampling and the oversampling technique, where we try to find out a balance between both and synthetically generate more data. The other algorithmic approaches, what we can also do is like the cost sensitive learning. Like whenever our model is looking out to the majority class, we can make the loss to be much more highly penalized, such that whenever it is trying to predict for the majority class, then the loss would be quite less. And if it is trying to predict for the majority class, then we can say that the loss to be high, so that it in a way tries to be strict for my minority class. That means whenever there is an occurrence of 0, my model should be much more overfit for that particular thing. So in that, what we do is the cost sensitive learning. And the other are the ensemble methods, like the ensemble methods which I generally talk about, like the random forest, gradient boosted trees, or AdaBoost. So they are built in such a way that they are not, they can handle the class imbalance on its own. And also like a class weight parameter in some of the algorithms like the support vector machine, where we can give a weight to the underlying distribution within the particular data. So based on the probability, based on the occurrence of the minority class to the majority class, I can give that as a weight into my model. Okay, that this is how my distribution is. So make the loss function in such a way so that it is much more robust to class imbalance techniques. Or the other things what I can change from my evaluation criteria is, so there are three parts of it. One is on the data front, you can change it, or on the modeling front, you can change it, or on the evaluation front. So from data front, what we did, we looked into the resampling techniques. Okay. And while trying to build the model, we have changed it from the algorithmic approach. Like we have made the cost function to be stricter for the minority class, or trying to build the ensemble methods. And the other thing what we can do on the evaluation front is we can tune our evaluation matrices in such a way so that whenever it sees a 0 or whenever it sees a 1, it would give much more penalty to it. Okay, like the F1 score, area under curve, and precision recall curve. Okay, and accuracy is mostly suggested to avoid, because whenever we try to calculate the accuracy for a particular class, if it is predicting correctly, then we say that the model is not that efficient. Let's see an example of this. Let's build a confusion matrix. Okay, so say this is actuals and this is predicted for me, and actuals 1 0, predicted 1 and 0. Suppose say I have got 100 samples, right? So out of the 100 samples, suppose say 99 belongs to, sorry, 90 belongs to the class 1. Okay, and out of that it has correctly predicted that to be as uh, that to be as correctly predicted that to be as class 1 also. Okay, and out of this, which is actually 1, and it has misclassified 10. Okay, and for the other class, suppose say there were like 5 samples. So totally, suppose say there are 10 samples. Out of that, it is correctly predicting as 1 and incorrectly predicting as 9. It has misclassified. Okay, so if I calculate the accuracy of the particular model, how much that would be? True positive plus 2 negative by all the values. So 90 plus 1, 91 by all of this. 90 plus 10, 100 plus 10, 120. If I do this, then how much my value would be? 91 by 120. It is 76%. So what I would say, my model is 76% accurate. Given that it had, like for the majority class, it had predicted all of the classes to be true. So my accuracy is coming higher. But in reality, for my other class, it is not correctly able to classify. So 9 samples, it has misclassified as true, although it was false. So this is how like a class imbalance can hamper my model performance if I look into the incorrect matrices. So to tackle on that, what we have to do is we should not go with accuracy, we should go with the other scores like the F score, where F score is the harmonic mean between precision and recall. And the other things like the feature engineering, suppose say we can drop some of the features, or we can create some of the other features which can be combination of multiple features. So this is like an example of how like class imbalance is done. Suppose these are cats and these are dogs. So in oversampling, what we do is we try to replicate more of the minority class. So for dogs, we have treated more sample of dogs. In undersampling, what we have done is for the majority class, we have decreased the samples which were there in the majority class. Okay. And in data augmentation, what we can do, like in the case of SMART or ADASIN technique, we are trying to replicate or generate more amount of data. Although we don't have like particular example of dog, but by looking into similar examples of dog which are there, we can create much more examples which are similar to dog. So these are the different breeds of dog which we had created. Okay. Any doubts till now? Okay. So coming to the next thing of hyperparameter tuning. So in that implementation of the decision tree random forest you had seen, right? There are different hyperparameters which can play a crucial role in how a particular model would behave. Okay. So like in any of the model, there are some of the parameters which are there. So the parameters are what we know and what we are, which we are not directly controlling. So suppose say the beta in the linear regression or in the logistic regression, right? So beta is something which is dependent on the loss function. how we are finding the loss function, how we are minimizing the loss function. Through that way, we can estimate the best beta. But some of the other parameters like the alpha, which is the learning rate. So on top of alpha, we are not doing any of the strict control as how much alpha should be, whether that should be high or whether that should be low. Given that alpha is influencing my model performances, how fast is my model converging or how slow is my model converging. So these all things which are non-tangible and can't be controlled from directly, like we can play around and that can affect the model performances, are known as the hyperparameters. Like these are parameters and these are hyperparameters. So the examples of hyperparameters in case of a decision tree is the maximum depth, like how deep the tree can go, because those are not explicitly what we say while building a tree, but we can play around and put a strong threshold on top of it, because we know if a tree goes much more deep, then there will be chances of overfitting, and the number of samples split, the minimum number of samples required to split an internal node. Okay, the minimum samples in a leaf, the maximum features, and the criterion like the Gini index or the entropy, which one to use and when to use what. So all these hyperparameters, whenever you are trying to implement any of the uh, modeling techniques, first go ahead and learn about what are the different hyperparameters which are there for my particular model. And based on that, get an understanding as how each of the hyperparameters play a crucial role in my model performance. And using those hyperparameters, you can build a robust model. So there are different techniques as how you can hyper tune or do the tuning of your hyperparameters. So one is the grid search, like you have just specified, say like my tree can go deep till say one level, two level, right, or three level. So based on that, my model would iteratively pick up. So for maximum depth of one, it would try to build a decision tree, and based on this, it would try to find out what is the absolute loss which I'm getting, or the absolute mean square error that I'm getting. Is that what is that particular mean square error for when the depth was 1? Okay, and similarly when the depth was 2, it would try to build another decision tree and get the mean square error. So using all those values for each of the evaluation matrices for different uh, hyperparameters that I have built, it to try to find out for which of the combinations of the hyperparameter is my total loss minimum, and based on that I can pick up that particular hyperparameter. Okay, so in grid search, it is a normal like a thing where we are randomly specifying in a particular grid, and our model iteratively goes through that in a particular. So we are defining this as a matrix, and in a particular matrix, it would go like for this is for depth, this is for the number of nodes in a leaf, this is number of samples in a leaf in a tree. So that is how it will iteratively go and iteratively build a particular model. In random search, in place of defining it as a grid, what it does is it tries to pick up one sample from each of the particular uh, values of the matrix. So in grid search, what happens is it is quite slow, given that it needs to go say one first row, second row, third row, first column, second column, third column, kind of a iterative fashion. But in random search, it randomly searches through the matrix and randomly picks up the value, and based on the number of iterations that I have, suppose I have got 10 iterations. So in 10 iterations, it will try to find out which is the minimum which is getting for each of the combination of hyperparameters, and then that would be my best parameter. The other is the Bayesian optimization. So in Bayesian optimization, we follow the Bayes theorem, and based on that, we try to find out what are the different hyperparameters based on the prior occurrence of the particular hyperparameter value and their influence on my model performance. Okay, this is the process how you can build your Bayesian optimization for hyperparameter tuning. Let's see an example of how this is done on the same data set what I already have for the random forest classifier which I had already built. Let's build a grid search CB. Okay, let's build a basic this. So for the random forest classifier, if you would see, if I look into the hyperparameters, these are the different hyperparameters which are there. The criterion, whether it is Gini index, the maximum depth, the minimum sample split. So these are the default parameters for the So these are the default parameters for the maximum features is square root. So these are the default features for a basic random forest classifier, like vanilla hyperparameters. So for maximum efficiency or maximum value, if you want to get out of the particular model, you need to tune this particular hyperparameters what it has. So here also, like if you go to the documentation of random forest, these are the different, this is the definition, and these are the different parameters it has, and what does each of this particular mean. Okay, like criterion is Guinea or entropy or log loss, and default is Guinea. And the maximum depth, it takes only integer parameter, and the default is none. So, and minimum sample split. So what does this mean and what value it takes, like integer or float? So similarly, all of the features, all of the hyperparameters for a particular classifier or regression, you will get in the documentation, and from that you can play around with that, or based on your intuition, you can give those particular values and see like how they are impacting my model performances. Okay. So suppose say I have taken the grid search CV. I am building a particular parameter grid. Okay, the number of estimates it estimated to be 50, 100, and 200. Depth is this, sample split is this, sample leaf is this. And on top of it, I am building this particular model. Okay, so based on the cross validation of 3 times, I am trying to find out which are the hyperparameters which should reduce my error value. So after fitting all of this, I am getting the grid search dot best parameters and grid search dot best estimator. So the best parameter, like maximum depth, was none, minimum sample split is 1, and this is what out of all the values what I had given. So out of estimators of 50, 100, and 200, it says that for 50 the error was coming as good, and for sample split of 2 it is coming as good. So by using the best parameters in back into my model, I will retrain my model again and try to predict my output. Okay. So after doing that, so given that this is a small data set, the output is, I think I need to rerun it again. So generally, like hyperparameter tuning takes a good amount of time, given that it needs to look into the sample space and try to find out which are the best estimator. So given that it was a small data set, so the accuracy is still the same and all those validation matrices are still the same. Otherwise, it would have been different. It would have been a bigger data set. Okay. Similarly, if I do this on the random forest regressor, okay. So this was the classifier which I had built. Suppose I am building another data set where my target is the grade. Okay. So this is not a classification problem. This is a regression problem. And on top of that, I am trying to do the grid search CV. Similarly, when I have done that, it would give me the best parameters and the best output also. Okay. The other technique which I can do is like these all techniques are available in the scikit-learn, scikit-learn.metrics, scikit-learn.model selection. All these are available, but the Bayesian optimization is not directly available in scikit-learn, but in scikit-learn optimization, sklearn optimization. So from that, I can select the Bayes search CV and build another model on top of it. So these are the various parameters which I had given, and based on that, it would try to build a particular model for me which would give me the best values. So out of that, I have built that particular model, and it was a regression problem. So the R square is coming as 0.97, which is quite good. Like it is coming near to 1. And the mean square error is also 5.6. Okay, if I take the square root of 5.6 is near to 2 point something, 2.36. Okay, that means my output is in the range of the error is in the range of the output that I have. That means it was 90, 85, 80. So the variability was like on an average, plus or minus 2 it is giving. So that is how you can play around with the hyperparameters and can build a particular model on top of it and see like which of the hyperparameters are coming much more important and how they're influencing my model output. So I think that's all for now what we have. Any doubts? Hello. Yeah, Shoaib. Hello. Anyone
Yes, sir.
else?
You are
Yeah.
audible. If, if anyone has any doubt, they can raise their hand.
No one has any doubt? Okay, then I think I will be supplying all this material back as well, the set of notebooks that I have back as well. And I think the team had also prepared some of the materials for this week, the code along practices, which I think you guys can go ahead, build the linear regression, logistic regression, all those models, random forest, and see how the validation matrices are coming for each of the particular model and get an idea of the working around all of those. Okay, Ayush, I think we can drop off if there are no other questions or no other queries for today. Archit, can we drop off? Or
Yes, sir, we can.
okay.
Thank you.
Okay then. Thank you guys.